Okay, are you ready? It's the final lecture for Chem 100. I'm so excited. I haven't fed the dog or the cat so that you might get some cat and dog noise on your last lecture because I know how much you love them. All right, we're going to finish off with a little bit more about gases. And basically, we have one more gas law to talk about, and that's the ideal gas law. And the thing that distinguishes this from what we did before is that there are no changes in variables. We call the ideal gas law an equation of state. All right, which means that you're stating the conditions. Here's the pressure, here's the volume, here's the temperature, what's the amount? So no changes in the variables, just an equation of state. And then we're going to do some gas stoichiometry because stoichiometry is your life. Alrighty, let's get started. Oh, there comes the cat. All right, so as I said just a moment ago, all of the gas laws we've studied so far involve changes in conditions. We have been holding the amount constant up until now, except for when we did that Avogadro's law one, but it is intuitive that as the amount of gas increases, pressure increases, and so on. And according to Avogadro's law, if pressure and temperature were kept constant and we increase the amount of gas, then the volume must increase to keep the pressure constant. So wouldn't it be nice if one equation took care of all the variables? And yes, drum roll, that equation is the ideal gas law. So there's our P, there's our V, there's our temperature, and our amount. R is a proportionality constant, but you could solve for it if you took the pressure times the volume over N times T for an ideal gas. They're all in there, and the value of R is right there. That's the one we're going to use. Now there are different R, depending usually on the pressure. Since we have so many different units for pressure, then you have different R's. Now you do have to pay closer attention to the units. So R is your key to that. Volumes need to be in liters, pressures need to be in atmospheres, and of course, as always, our temperatures need to be in K, in Kelvin. All right, so all the gas laws are in there. Check it out. So PV, there's Boyle's law. If I kept volume constant and so I take that out and I varied the temperature, then if I took temperature to the other side, so P over T equals essentially R because both volume and amount are being held constant, and so on. So all the gas laws that we've studied are essentially represented by the ideal gas law. The relationships are still the same. Okay. All right, stoichiometry of gases, and then we'll do some problems. Well, I already kind of set the stage for this in the last lecture. That volume as coefficients idea, okay, is going to be used here. Now, there are two types of, and I kind of go through this very quickly in this small paragraph down here, but there are two types of gas stoichiometry problems. When you're at STP, life is good because we can use the molar volume and we don't have to plug into the ideal gas law. So if I want to go between, when we do a stoichiometry problem, let's say A is a gas, B is a solid, and C is another gas. Okay? Get myself some room here. I'll get it back. Hold on. If we're at STP, if we are at STP, and I know I have 5 liters of A, and I want to know how many grams of this, well, all I have to do is use the 22.4 thing from the mole chart by multiplying, okay, times 22.4. I get to moles, I do my mole to mole thing, and then change back to grams. Even better is if I am comparing two gases, and that would be A and C in this example. Then I can use the coefficients and I don't even have to convert to moles. So that's great. So if this had a 2, if A had a 2 in front of it and C had a 3, and I'm comparing two gases, all I have to do is say 5 liters times 3 over 2. Now, that actually doesn't matter if you're at STP. As long as they're at the same conditions, I can do that. So I guess I lied. There are 3 types of gas law problems. There are the ones that are at STP, and you can use the molar volume to get into moles and get back into volume. There are just gas, when you're just comparing gases, as long as you're at the same conditions, you can use the coefficients to move in volumes. Okay, so that's 2. Well, the third type is when you are not at STP, and you are comparing and you're using a gas. Let's say that you do something like this. We start with 5 grams of B, we turn it into moles, and the question is, what's the volume of the gas? And I'm at, let's say, 100 degrees Kelvin and 2 atmospheres. Well, that's not standard temperature and pressure. So what I would do, it's my usual stoichiometry thing, get to moles, move using the coefficients, and then to do this step here, I have to use the ideal gas law. So applying, and there's my moles, you were given the temperature, you were given the pressure, and you calculate the volume. So those are the types of things we can do with, now that we know some gas laws and we know how to do stoichiometry. All right, so let's do some practice. All right, number 1, what is the pressure? You're given a volume, you're given an amount, you're given a temperature. You have no changes. This indicates, before I start writing, let's give some room here. This indicates that we need to use the ideal gas law because I have no changes in my variables. All right, so PV equals nRT, and we are solving for pressure. So pressure is equal to nRT over volume. Okay, remember you have to pay attention to units. We're good with moles. We're good with those liters. Oh, R's next, sorry, 0.083 or 821 liters atmospheres over mole K times the temperature, 325, already in Kelvin. How nice. Okay, so the K's cancel, the moles cancel so far, over the volume, which is 20 liters. And the liters cancel and I end up in atmospheres. So when I plug that into my calculator, and then divide by 20, I end up with a pressure of 0.911 atmospheres. So 0.911 atmospheres is my answer for number 1. All right. Find the molar mass of the gas. All right, let's give ourselves some more room. Don't worry, we'll get back that stuff that was there. And we need to talk a little bit more about what we can get out of the ideal gas law. So, molar mass, where would I find that in the ideal gas law? Get back my writing. Well, PV equals nRT. N is moles. Molar mass. I can get moles when I take mass and I divide by molar mass from the periodic table. Remember from our mole chart, when I go from mass to moles, I take that mass and I divide by what's on the periodic table for the molar mass, right? Well, that's what we're going to do. We're going to take the mass in grams, given here in the problem, and we're going to divide by the molar mass, and that's what I'm going to stick in the N spot for, I'm going to solve for N, which is moles, and then I will use this to get my molar mass. So let's leave that right there, okay? This is what I don't know. I'm going to get this from the ideal gas law, and I was given this, okay? So we're going to solve for N. N equals PV over RT, okay? Pressure is not in atmospheres, so I'm going to take the 753 millimeters and divide by 760, go back up to, this is lecture 23, 21 at the end, and you have all of your conversions of pressure units in the lecture notes. 0.99 atmospheres, okay, times my volume, which it needs to be in liters, 0.117 liters, changing those milliliters to liters, divided by R, 0.0821 liters atmospheres per mole K. It's a mouthful. Times my temperature, and it's an 85 degrees Celsius, 85 plus 273.15, and I end up with 358.15 K. The kelvins cancel. I'm going to end up with moles because I'm like 1 over moles, which is moles. Atmospheres cancel, liters cancel. Okay? So 0.0821 times 358.15, storing 0.99 times 0.117. And I get 0.00394. N equals 0.00394, or moles, 3.94 times 10 to the minus 3 moles. I'm going to do that one more time to make sure I did it right. Same thing. All right, so that is my number of moles. I'm not finished. Let me give us some more room. I'll get it back. Okay, now that's not what they asked for. They asked for the molar mass. So let me write it again. So mass over molar mass equals N. All right, so I'm solving for this. All right, so mass equals N times molar mass, and getting molar mass by itself. So mass, and that makes sense, divided by moles equals, so I could have done it completely from the units. Mass is in grams, so 0.555 grams divided by the moles I got from the ideal gas law. So there's my grams per mole. And we end up with 140.86. Molar mass equals 140.86 grams per mole. So using the ideal gas law to solve for molar mass. All right? Number 3, I see moles, I see a temperature and a pressure, and we're solving for volume. So it looks to me like an ideal gas law, but solving for volume this time. I encourage you to go ahead and turn off the video and try it. So volume equals nRT over P. So there it is right there, up here at the top, and I'm rearranging to get volume by itself. 0.25 moles times 0.0821 liters atmospheres per mole K. times temperature, put it into Kelvin, divided by the pressure. Well, I cannot draw a straight line with this pen. And it is in atmospheres, 0.974 atmospheres. Atmospheres cancel. I'm looking for volume. Moles cancel. K's cancel. Okay. And I get 6.18 liters. Okay. I think that's enough messiness on one screen, so I'm going to go ahead and scroll so we can get to our last couple of problems. All right, so number 4 looks like an ideal gas law to me. Volume, temperature, pressure, how many moles? Okay. And then looks like some stoichiometry problems. So before we get started writing, I'm going to do a little scrolling to give us some room. Whoops. Put that finished down just a little. All right, so let's do that ideal gas law one more time, and then we'll do a couple of gas stoichiometries. So PV equals nRT. N equals pressure times volume divided by RT. Pressure is already in atmospheres. That's good. Times the volume. Put it in liters. And my temperature, 24 plus 273. And I get 297.15. K's cancel. I'm looking for moles. Atmospheres cancel. Liters cancel. And I get 0.0157 moles. Alrighty, number 5. How many moles of water are required to form 1.8 liters of oxygen at 325 K, and so we're not at standard temperature. We are dealing with liquids and gases, so we can't use the coefficients to compare. So stoichiometry, if you're not in moles, get there. Well, I'm going to have to use all of this to get into moles, and that means ideal gas law. Solving for moles like we just did. Okay, so N equals PV over RT. Pressure, and I'm going to leave off units, guys, just for, space sake and speed. I think I've shown you that the units work out. At least we didn't have to do any conversions. Okay. All right, I end up with N as 0.0729 moles All right, so now I have gotten into moles. Put it down here. And now I'll do my mole to mole step, mole ratio. And I get 1.146 moles of water. And that was what we were asked for. All right, one more question. Now you know you're going to get plenty of practice with your recitation and your sapling and the exam review before you have an exam on this. These last two lectures is the easiest material in the last three is the easiest material in this last set. Those first couple are, the ones you're going to really need to spend some time on. All right, so let me get some room here by scrolling one last time, and then we will be finished. All right. All right. Oops. Oh my goodness, we have to write an equation. Say it isn't so. So we've got to do how many grams of oxygen gas, complete combustion. So let's write our combustion equation. All right, so we got a hydrocarbon with some oxygen, making, as always, CO2 and water. 7 carbons, so 7 CO2s, 8 hydrogens, so 4 waters. 7 times 2 is 14, plus 4 is 18, so 9 oxygens. How many grams of oxygen gas are necessary for the complete combustion of 94.5 grams of toluene? Now this is not going to involve any gas loss. But let's go ahead and work the problem. We're going to get into moles. We're going to do our mole to mole thing. My mole ratio here is going to be 9/1. We'll get some new moles, and then we're going to convert back to grams using the molar mass of oxygen. I need the molar mass of the C7H8. And that is 92.08 is the molar mass. So 94.5 divided by that. All little over a mole, 1.03 moles. And then times 9, mole ratio. And I end up with 9.24 moles times 32. So the answer to A is 295.6 grams. All right, for A. B, what volume of oxygen would be necessary? Now we're at STP, so I can use the volume of a gas, moles, multiplying times 22.4 liters per mole. So all I need to do is go to this moles of the oxygen and multiply times 22.4 liters per mole. And I can only do this right here when I am at STP. Okay? Only. Standard temperature and pressure. Okay? Times 22.4. And the answer to B is 206.9 liters. Okay? And C, what volume of oxygen would be necessary for this same reaction? So now we're not at STP, and we need a volume. We have some moles. Gonna have to use the ideal gas law. So for C, volume, solving for volume, volume equals nRT over P. Moles is 9.24 times 0.0821. Boop. Times 50 plus 273, 323.15. Off my screen there a little bit, divided by the pressure, which is 3 atmospheres. Okay? Times divided by 3. And I end up with 81.7 liters. All right, so standard temperature is 0 degrees Celsius. But then I went up to 50 degrees Celsius. Volume and temperature are directly proportional, so smaller temperature. Does that make sense? Let me check those calculations again, because that doesn't make sense. We went up in temperature, so we should be going up in volume. Okay. All right, let's try this again. But it's at a different pressure too. I still get 81.7. So I went way up on my pressure. So the volume went down. All right. Okay, so there's the answer to C, our last problem. Thank you for putting up with my lectures this semester. I have learned a lot from doing this course in this format, and I hope that you learned a lot about how to be a more self-guided learner. I know that this format is really different for a lot of you, and I appreciate your patience. Thanks.